Welcome to the future of chemistry education. In this video, I will introduce an experience designed based on augmented reality technology, AR Chemistry Experiment Classroom. Now, let me introduce the design of the entire experience. In the first part, I will introduce the research background. By studying the papers of Professor Jonah and others, we can understand that using AR in the classroom can bring better teaching experiences, help teachers visualize knowledge points, and help students in better understanding knowledge. However, in reality, chemical laboratories face the following problems: a lack of laboratory resources and difficulty in disposing of waste after experiments. Some dangerous experiments are difficult to conduct. Microscopic chemical changes are difficult to observe. And now, AR technology can help solve these challenges. The second part is the experience design carried out in conjunction with the idea card. Firstly, I use pre-designed 3D models to bind teaching cards and showcase chemical models. Afterwards, connect the model with the position in real space. Then, some gestures can be designed to move the model and simulate the process of chemical experiments. At the same time, there may be some challenges encountered in the design. The current design meets the needs of chemistry classroom teaching and is not an unrealistic design. Secondly, the experience conducted using AR may have differences with the real world, which requires continuous analysis and improvement. The next part is prototype design. The entire AR application was developed using Unity and Vuforia frameworks. I modeled the chemical models and experimental regions that need to be explained in the chemistry class and created special effects during the reaction. There are model cards that will be used in the application, and they will be used in conjunction with the classroom content taught by the teacher. Next, I will demonstrate the prototype function from a first-person perspective. This interface is the entrance menu of the application, with 3 options corresponding to element display, experimental content, and a video classroom function. In the first scenario, we can see the micromorphology and changes of chemical substances. When the teacher explains the structure of chemical substances in the class, we can use the application to scan teaching card to see the microstructure. Combined with other element cards provided by the teacher, we can observe changes in combination. When elements approach, they will react to generate new molecules. We are able to move and observe microscopic models up close. In addition to the basic material structure, we can also construct more complex chemical models for students to carefully observe and learn about the composition and connection methods of complex molecules. In the second scenario, we can observe macroscopic chemical reaction phenomena. The teacher explains the relevant knowledge points of chemical reaction and provide chemical reagent cards. We can scan the cards to observe the color of the reagents. When the reagents are mixed, new compounds will be generated and the color of the reagents will also change. We can also conduct more diverse microscopic experimental observation in the scenario. In the third scenario, we can choose the teaching video uploaded by the teacher to learn the experimental process.
Today I'm going to mix liquid mercury and liquid gallium together, because both of these metals possess the unique ability to form compounds with other metals. Here, for example, it looks as though the mercury is consuming the gold.
And this is a video about dangerous operation.
That was a piece of lithium exploding, the metal whose salts are commonly used in batteries. Lithium is an incredibly lightweight metal with a very high energy density. This piece here weighs just 7.
The next part is testing and evaluation. During the test phase, I invited several classmates to experience different scenarios. We use mobile applications to test the functionality of each scene under different lighting conditions. We have designed different test cases to prevent missing scenarios, verified the different functions of the application, tested operability and sensitivity, and identified disadvantages in the demonstration plot for different lights, angles, card combination, and gesture operations. Under various tests, the current application is able to run its functions fully and performs well. And then, we discussed and summarized several advantages and areas for improvement of the current experiences. Firstly, a microscopic model can make the experimental process clearer, and the characteristics of the model are in line with the knowledge points in the classroom. The entire experience is smooth and the card recognition is accurate. In addition, there are some aspects that can be improved, such as the lack of dosage control in the experiment and insufficient experimental complexity. The recognition of model needs to be done in a clean and tiny environment, as a clogged environment can affect accuracy. Lacking some high-risk experimental content, the type of experiment can be expanded. The fifth part is reflection and future challenges. Based on the entire design process and testing analysis, I have analyzed the directions for future improvement and development of the current application. Firstly, the richness of the scene and plot can be enhanced. We can place different 3D models in real environments and interact with them while moving. We can also design storylines and levels based on the course knowledge points, allowing students to enhance their learning effectiveness through storytelling experience. We can also improve the technology and user experience. For example, combining high-quality AR devices using headsets and controllers and so on brings more sensitive operations. Clear guidance steps can also be set in the scene to build higher definition models and enhance visual effects. This AR chemistry classroom prototype demonstrates how augmented reality can address critical limitation in traditional science education. By enabling interactive visualization of molecular structures and safe simulation of reactions, the technology provides access to experimental learning opportunities that would otherwise be impractical or impossible in resource-constrained environments. In practical applications, we have found several highlights. Students can see changes at the molecular level, which greatly reduce the difficulty of understanding. The simulation of dangerous experiments ensures safety and does not distort reality. Instant feedback mechanism makes the learning process more efficient. Of course, any new technology needs to be constantly improved. We believe that with the continuous interaction of technology, AR will become an indispensable tool in chemistry teaching, bringing teachers and students a safer and more efficient teaching experience. Thanks for watching. Let's explore chemistry beyond limits.